into a wide areas, such as bioimaging, energies, for sure, optical fibers, energies, and also based on phosphor or emitting systems that are used every day. One of the last also application of the lanthanide luminescence is lanthanide thermometry. That is one of the most specific and non-contact technique to measure temperature. But today I will show you mainly our research based on lanthanide 3 emitters, looking forward to achieve white light emitters in single component. In order to achieve this, we have done the synthesis and characterization of a family of dinuclear complexes, and we have been working with 3 main lanthanide cations. I will begin with dysprosium 3 species that show one of the interesting results. The synthesis of these kind of dinuclear compounds is, in the first step, we have done the synthesis of different ligands with different substitutions in these positions, where we have introduced some methyl groups, chloride groups, or methoxy groups in order to influence the excited electronic levels of the ligands that, as we will show during the presentation, are the ones that are involved in an electronic process that produce the light that it is emitted. In this case, we have synthesized this ligand that possess 4 donor atoms, 2 nitrogen atoms, and 2 oxygen atoms. This oxygen phenol group are deprotonated in the synthesis, and these 4 donor atoms are coordinated to the lanthanide cation, as is shown in this diagram. We can see that these 2 nitrogen atoms are coordinated to the metallic center. The oxygen of one of the phenolic group is directly coordinated, while the other one is bridging the 2 metallic centers. The metallic center presents an octa-coordinated environment where I have mentioned 4 coordinated atoms so far provided by the ligand. Other 2 atoms are provided by a bidentate ionic nitrate molecule and also a coordinated solvent molecule. We have defined this as solvent molecule only because we have obtained this compound with methanol in the first coordination sphere and also with dimethylformamide in the first coordination sphere. So this dimeric compound is built based on this lanthanide 2 oxygen 2 unit, where we have a central symmetric point. So these are 2 absolutely symmetric units. We have obtained the single crystal of these compounds, and we have obtained the structure of these molecules based on this ligand that I have presented before. The diagram is a little bit harder to understand and to observe clearly. That's why I have presented and described the environment of the dysprosium cations in the previous slide. So the characterization of these compounds, in this case, I will present mainly the optical characterization of these compounds because we are interested in to produce new materials, trying to achieve white light in an efficient way, trying to reduce cost and reduce the materials that are involved in the process of these emitters. At the right, in the figure B, we have the emission spectra of the 4 complexes that I have presented before. And in the left side, we have the excitation spectra of the same complexes. Every data is recorded at room temperature and in solid state. It is important to highlight in the emission spectra that we have the contribution of both the ligand, that is this broad band, that is kind of the background of the emission spectra, and we also have these sharp bands that are due to the excited electronic state of the 4F cation. Here is described every transition that must be associated with each band, okay? And here we have the excitation spectra monitoring the emission band at 565 nanometers. And here we can have, it is interesting to show that in the excitation spectra, we have mainly the bands due to the absorption of the ligand. This result is very important because we are proving that the emission of the 4F cation is actually based on the well-known antenna effect, where the ligands absorbs the light, and in the excited state, the energy is transferred to the 4F cation, and finally, you have the emission of the 4F cation and also the emission of the ligand if the energy is not fully transferred for the excited state of the lanthanide cation. We are also interested in to check the temperature dependence of the emission spectra of these complexes. These measurements could bring interesting information due to the excited state of the cation and the relation with the excited state of the ligand. If these energy levels are close enough, they can be thermally populated and the emission spectra can be influenced. But as we can see, only one of these compounds, this phenomena seems to take place. In the other complexes, the emission spectra doesn't present much change in the measured temperature range. In this case, we have collect data from 25K approximately until room temperature. Other information that can be extracted from these experiments is the integrated areas of the different transitions. In this case, in the dysprosium cations, mainly two bands are analyzed, and they are named mainly because of the color that these bands emit. In the case of the transition of the 4F 9/2 to the 6H 13/2, you have the emission band that lies close to the yellow color. And this is why you have the Y band. And the other emission band lies close to the blue color. This is the reason why you have the B band. And you can normally analyze the integrated areas of each transitions or the ratio of the two transitions. We can see here that only the complex 1 that present the methanol molecule in the structure present this weird behavior and increase the ratio at room temperature. So we can conclude that the presence of these small molecules influence the properties of the dinuclear complexes. And the most important part is that you, from the emission spectra of these complexes, you can calculate the coordinates of the Commission International. That is the common base where you can conclude or can compare which color exactly is emitting your system. You can find this in literature, and there are different procedures where you can follow to obtain these calculations. In this case, most of the emission complexes, mainly for 3 and 4, the emission of the complex lies exactly in the white color coordinates. And why is this? Actually, this was done by strategy, by planification, the different techniques that are used to obtain white light. To obtain white light, there are mainly 3 approaches that can be done. The most basic one is to use a dichromatic approach, where do you need 2 colors to produce white light. In the dichromatic approach, you need a blue emitter and a yellow emitter. In this case, the blue emitter will be mainly the ligand, while the yellow emitter, it is the dysprosium 3 cations. Actually, we have obtained this in a very precise way, but the quantum efficiency of these complexes was a little bit low. So we're working now in the next step, that will be the trichromatic approach, where do you need now 3 light sources to produce the white light. You need blue, that can be again the ligand, and you need now a green emitter and a red emitters. And here is where they come, the work that I will show now, based on terbium 3 cations, that are the green emitters. And we are working on the europium 3 cations, that will be the red emitters. So we basically follow the same procedure that I showed before, based on the dysprosium 3 cations, but now with the terbium 3 cations. And in this case, we have obtained also a 4 complex, but now with a carboxylic group. This ligand was also made to react with dysprosium 3 cations, but we couldn't characterize well the obtained solids. That's why I didn't present the last results in the dysprosium complexes. But in the terbium 3 complexes with this ligand, we also could obtain the molecular structure. We obtained suitable single crystal from the solution with DMF, and we did the characterization. And we have the same structure that I have shown before. So I will not give further details. Now, when you look at the emission spectra of these complexes, now we can see mainly the emission bands only due to the 4F cation. In this case, we didn't observe the emission of the ligand. That will imply that the energy transfer between the ligand and the terbium cation is more efficient than the energy transfer between the ligand and the dysprosium cations. And for sure, in the excitation spectra, we observe the absorption bands due to the ligand. That will show again that we are producing the emission of the 4F cation through the antenna effect. So we did again the temperature dependence measurement of these complexes, and now in the terbium 3 cation, the bands are denominated green and blue, again because of the energy that the emission band lies. In this case, for sure the nomenclature is different than in the dysprosium 3 cation, but you have the emission bands in green and in blue. Here are highlighted. In this case, you can see that the integrated area of the emission spectra of the compound in red in this zone shows almost a linear dependence with the temperature. That will imply, in this case, this compound could be also used in thermometry. Okay, you can obtain most detail analyzing each band because the ratio is almost constant in the whole temperature range, but you have different possibilities to analyze the temperature dependence of these systems. In this case, we have measured the quantum yields efficiency of the emission spectra, and we have found some really high values and interesting results, mainly with the compound 4, that was the ligand with carboxylic group that we could not obtain with dysprosium 3 cations. In this case, we have a quantum efficiency of near 17%. The quantum efficiency is important to remember that for sure is a ratio between the emitting photons and the absorption photons that are calculated from the reflectance spectra of the sample, okay, and the standard that you are using. And the emitted photons for sure are calculated integrating the whole emission spectra. So as we have obtained these interesting results with terbium 3 cation, it's important to summarize what we are doing specifically. So we have these dinuclear complexes with this functional group that we are always modifying through the different ligands. So actually by the modification of this functional group in the ligand, we are actually tuning the energy levels, the excited energy levels of the ligand that plays an important role in the energy transfer through the 4F cation that emits finally. In this case, the best compound, the properties that were the best are for the compound 4 and are highlighted here at room temperature with a high quantum yields with lifetimes in the millisecond range, with color in the green region. And it is important also that easy because the emission is mainly based in the sharp band of the 4F cations, the color purity is close to 99%. So the quality of the color that we are obtaining is really high. So finally, in order to seek for an application of these complexes, we're working now in the preparation of thin films of polyurethanes doped with these complexes. The preparation is by slow evaporation only, and you can obtain some homogeneous film that I am showing here a picture. And under UV light, you can see this beautiful green bright emission. And in this case, only with 1% of content of the terbium 3 species, you can achieve now a photoluminescent quantum yield circa 60%. And this is being part of a master thesis of Danae Villagra that is working in our group. So finally, as I mentioned before, we are working now in the European species in order to achieve the trichromatic approach. Finally, I want to acknowledge the different financial support that we received to develop this research from Chile, from Brazil, and from France, to highlight the people that have worked in the research that I have shown now, and the people that is working also in the thin films. To acknowledge also this community that give me the opportunity to present in this lecture series, and that I met in June last year in Stockholm, where I was given this honor diploma. I was sharing this opportunity with the professor also. Finally, to introduce to you our working team, full of young energy, and also the people that we are working on from Universidad Federal de Goiás, Professor Ricardo, Professor Lauro, from Université de Rennes, Professor Natalie Odebron and Jean-René Amon, that is the director of the international program. And from the Institute of Physics from Sao Carlos, Professor Claudio José Magón, Professor Helmut Hecker and Karsten Dorenkamp that help us in other research. And for sure, we are a big team that work in the University of Chile.